mind because I talk too much. Have a lot of things I want to talk about today. But what I want to do, we're going to spend today talking about fatigue in general. Then we're going to go into specific fatigue defects. I'm actually going to go through and talk about all the different kinds of defects. I had a question on the emails as to why was I focusing on bending stresses, longitudinal stresses versus contact stresses. As we go through the different defects, you'll see that different defects depend on different stress states. And so we will, I'll try to address some of the, what are the differences between different types of defects and what they occur. But I want to get everybody's attention, so to speak. So I'm going to start off by talking about a derailment. If you remember the movie that I showed you last week, the Network Rail movie, which I think is a very good movie, and I like to show it because it gives a good overview. If you recall, the name Hatfield derailment was mentioned. And Hatfield derailment was a milestone derailment in the UK. It happened in October 2000 on a passenger train that was traveling. Let me get this going on here. There we go. There we go. So the Hatfield derailment happened in October 2000 on a passenger train that was traveling approximately 200 kilometers per hour when it derailed. Now, obviously, we're talking about rails, so it's obviously going to be a broken rail derailment. 4 passengers were killed and 108 out of 170 were injured. So more than half the passengers had some sort of injury or other on it. And in fact—
So what is the name of the lesson, please? The name of the lesson.
This is from broken rail derailments, but I'm just showing a few slides from this, and I'm going to jump back to where we left off last week.
Thank you.
But these particular slides are from broken rail derailments. So what was, in fact, if you, the report issued by the British government, the investigation report said that the only reason so few people were killed was because the structural integrity of the vehicles, what's called the crashworthiness, which we'll talk about in another lecture, probably in January. But the crashworthiness of the vehicles were very high. In contrast, there was a broken wheel derailment in Germany right around the same time, right around the year 2000, exactly the same speed, roughly 200 kilometers per hour, and there were 104 people killed in that particular accident. It was the worst accident in German railway history, and it was the only ICE derailment in modern times that. And it was catastrophic. And we'll talk about that also in January. We talk about broken wheel. But in that particular one, 104 people were killed because the vehicles were deemed to be have very poor crashworthiness. They were not structurally sound. And so that's an issue we'll get into later. But the Hatfield derailment was a major catastrophe for Network Rail. And it was completely unexpected. You can just show you a few pictures. Whenever you see vehicles off on the side, that's always bad news. Once vehicles are turned off fall off on the side, people are seriously injured, killed, whatever. It's a bad thing that's going to happen. Here you can sort of see the makeup of the train. It was a catastrophic failure. The ones were killed were in the Mark IV restaurant coach, which had particularly good crashworthiness, which is why so few were killed. But even so, the force of the impact at 200 kilometers per hour was very significant. Now, let me go ahead and I'll come back. So it was a fractured rail. This is actually after the thing fell apart. This is what it looked like, but it was actually a detailed fracture from a shell, which we will talk about today. And we'll spend a little bit of time talking about what this means, because this is one of the most common types of defects. What was particularly nasty about this particular defect was it was not detected by the ultrasonic testing that was done shortly before the vehicle came, because at that time the procedure used by Network Rail for ultrasonic testing was very poor. If you look at a rail, the defect that actually caused this was over here in the gauge corner of the high rail. So this is the outside rail. This is where the wheel curves. Remember, I showed you that very nice high stress concentration that I showed you right over here? That was a direct cause of this type of defect. At the time, British Network Rail, the British railway system, didn't believe that they were subject to these types of defects, because at the time, everybody thought these were heavy axle load defects. Only the crazy Americans and the Australians and the Russians got these type of defects. You know, UIC railroads didn't get those defects. They were catastrophically wrong. And in fact, as we'll talk about it later when we go through the defects, we've even seen metros get these type of defects. So metros with axle loads down in the 12 to 14 ton range have been gotten these defects under certain circumstances. And what was happening is the Network Rail at the time was just ultrasonic testing down the top of the railhead, down the center of the rail, because that's where they thought all their defects would be. And they just weren't even equipped to test out here. Now, why do I know all this? I was actually part of the team that was brought in 2000 after this derailment to completely upgrade their inspection and maintenance procedures to make sure this never happened again. And we'll talk about that in another class. Right now, I just want to make this point. Now, what was particularly bad about this accident or about this type of defect is after they discovered that they were testing in the wrong place, they changed their testing procedure. They went back around the entire network and they found hundreds of these defects that were there. So this wasn't even a fluke. This wasn't even there's an exception to everything. There were hundreds of the defects they just didn't see because they weren't testing. They ended up slow ordering the railroad until they could repair it, because they just couldn't repair all those defects for months. And because of their contracts with the operating companies, remember, this is when Network Rail was an infrastructure company and the operating companies were separate companies. That's that structure we talked about in the very first class that we see sometimes in Europe and elsewhere. And now the British want to change it. They just came up with a report saying we should change it. But because of their contract, they generated 7 billion, that's with a B, billion pounds in penalties. So that's about $12 billion or about 40 billion shekels, to put it in perspective. It actually ended up bankrupting because at the time, it wasn't actually Network Rail. It was a company called Railtrack. That was the infrastructure company. They went bankrupt and they had to be salvaged by Network Rail. The firms that were doing the inspections had about 13 million pounds in fines. Manslaughter charges were filed against 5 rail executives, and it was not dismissed for 5 years after the event. It was a total disaster, and it changed the way Network Rail did everything from a track inspection point of view going forward. Massive changes as a result of this. So this was a groundbreaking derailment and accident in the UK. Broken rail derailments, and we'll talk about that. It's one of the largest causes of derailments. This says in the US, but I will tell you it's one of the largest causes of derailments worldwide. When we get to talk about accidents and distributions, which we won't do till January, you'll see that the UIC railways, the American railways, the Russian railways, the Australian railways, broken rails is consistently among the top causes of derailments. It still is today, even with our improved technology for inspection. It still remains a major source. Now, for those of you who said, like the British, that it's just a heavy axle load phenomenon. Those crazy Americans and the crazy Australians who run very heavy axle roads, they get what they deserve because they run heavy axle loads. This is a broken rail derailment that occurred in Washington Metro. So this is a metro. And again, I was actually called in to help investigate this particular case. This one started from a corrosion defect on the bottom of the rail. So underneath the bottom of the rail, actually on the other side of the rail, right over here, there was a corrosion defect, which acted as a stress concentration factor. Now, remember, under a wheel, your maximum tensile stress is in the base of the rail. Remember, I keep giving you all this esoteric theory, because the theory actually has a meaning when we start looking at failure mechanisms. So because we had a stress riser in the base of the rail, there was a crack that's initiated. Actually, I believe it started over here, sorry. It actually initiated over here, went through here, propagated through here, came down here, propagated through there, propagated up there, fractured the rail and under the train. And fortunately, there were no fatalities, only injuries that went to the hospital. But this was not the first broken rail derailment in Washington Metro, nor was it the only broken rail derailment in metros in general. Washington Metro, a number of years before, had a detailed fracture from a shell, similar to the one I showed you back here, which is this kind of defect. We'll take a look at that in much more detail today. And we know, I've seen plenty of UIC railway derailments where are broken rail derailments. So these things exist. And this is the reason why we care about this. When we were dividing up the course, Arkadi's told me that I should handle broken rails. So that's why you're getting all this heavy dose of rail fatigue and rail engineering. Okay, we'll come back to this a little bit later, but I want to now go back to where we were last week. Let's see. I believe this
Can I
is
ask a question, Professor?
yes.
How do you detect the corrosion in this cases?
The Washington Metro Safety Department asked me the exact same question, and I said, good luck. There are no technologies available right now that can detect corrosion underneath the rail. What you have to do is you really have to do a good job of ultrasonic inspection and catch those defects as they propagate up through the railhead, because ultrasonics will not find a small corrosion initiator on the base of the rail. A lot of times they're on the outside and you can see it, but not always.
Maybe sometimes, we can take a sample and dismantle one of the rail and then to put it back and to understand what's going on around the environment. Let's say if we are in a tunnel, for instance.
Yes. Well, actually, in a tunnel, you see corrosion. We'll talk about corrosion again today. Okay. But if you remember the movie, they showed actually some rail with some severely corroded bases. Those are fairly evident. And you usually you want to do something when you see something like that occurring. But that particular derailment that I showed you in the Washington Metro derailment was a real problem because there was no sign of corrosion from the top. You didn't just see any evidence of corrosion from the top, and there was nothing that pointed to that location. And there's no technology that can detect a corrosion under the base of the rail. In the olden days, back when there was a lot of manual and hand inspection, they actually used small mirrors underneath the base of the rail, but nobody does that anymore because nobody has the resources or the manpower to do that. That's just, if you suspect a problem, then you can start looking at that. Unfortunately, what happens is there are a lot of corrosion cracks that initiate, and not all of them translate into a rail defect. That's one of the problems. So, let me give you one statistic so that will sort of tell you what the issues are. In the United States, we have about 200,000 miles of track, 300,000 kilometers of track. We find 200,000 rail defects a year. Okay, on average, 1 a mile. So that's 200,000 defects per year are found. We find about 90 to 95% of them by ultrasonic inspection, and the rest are found by various techniques, such as the rail cracks and the signal system detects it, because if the rail fractures and it opens up, the signal system will detect that and go up red, or a good inspector will see a crack coming along and finding it. We still find tens of thousands of defects that way. And we get approximately 100 broken rail derailments a year in the United States. So that's 100 out of 200,000. So so we're at the 99.99% detection rate in terms of the ability to find the defects, but that 0.01% detection rate, or it's actually 0.005% detection rate, translates into about 100 derailments a year. So it's a problem that's still with us, and we're still looking to get it out another 2 decimal places. The same issues exist. Again, we're 99.995% effective in detecting these types of defects throughout the world. But unfortunately, in the railway industry, and we'll talk about derailments in January, it's the exceptions, it's a small number that sneak through that cause the catastrophic derailment. So, again, Hatfield, there were hundreds of detail fractures from shells in the track. One of them happened to have broken, and that caused a catastrophic derailment. But, when you get a catastrophic derailment like that, everything happens. Okay, so do I have the right one that I want here? Hold on a second.
Thank you.
No, I want this one. Oops, I know I had the wrong one. Okay. Okay, so so this is a continuation of last week's lecture. So this was what I call Rails A, for those of you who want to find it in the notes. So we're going to spend a bunch of time talking about different failure mechanisms. The 2 dominant failure or replacement mechanisms for rail are wear and fatigue. So what you're seeing here is classical rail wear. Again, you saw that in the movie. You see this again here. Let me get a highlighter up here. Okay, so rail wear. So this is the new rail section up here. This is a worn rail section such as you find in a curve. Why? Because we have side wear, which is most common with a curve. So we have side wear, which is usually you see on the outside or high rail on the curve, because that's where the wheel flange rubs against the rail. And then you have head wear, or top of head wear, or top wear, which happens on straight track as well as on curved track. You can see the type of rail. Wear standards take several different forms. You can have a separate head height wear limit and a separate gauge face wear limit. So for example, you can have 12 millimeters of head wear here, and you can have about 18 millimeters of gauge face wear here as a limit. It will vary with the size of the rail. Because if you remember, a 60-kilogram rail has a larger head than a 50-kilogram rail. So you can afford to lose more metal. And so the standards vary as a function of the size of the rail. So we also use a parameter called percent head loss. So percent head loss means if we calculate the area of the railhead nu, and the area of railhead is defined by this intersection point upwards. So this is the head nu, this is the head worn, and this particular case shows 38% head loss. So 38% of the rail is lost. And in this particular case, from this particular example, this happened at about 213 million gross tons. So remember, we were talking about 1,000 million and 1,500 million gross tons of fatigue life in a rail. And here we have wear life that can be down in the order of a couple of hundred million gross tons. And I mentioned the other mechanism, fatigue, which we will be spending a lot of time talking about. Fatigue is the development of defects, either totally internal to the rail, such as at Hatfield, or on the surface of the rail where you can see them, see partially, but usually never see the full extent of the defect. Okay, so if we look at, so the obvious question is, what do we replace our rail for? Which happens first, wear or fatigue? And the answer is it depends. It depends on where you are. It depends what you're doing. For example, this particular graph shows wheel load, static wheel load, as a function of life in millions of gross tons for wear versus fatigue. And what you can see here is for the lighter axle load. So if you take a UIC type of axle load, which is somewhere around here, you see wear tends to dominate, but we're getting close to fatigue. So wear or fatigue can happen in tangent track. If you take a North American type of axle load on tangent track, fatigue is far away the dominant life. It's going to fatigue at about 300 or 400 million gross tons, whereas it may not wear till about 1,000 million gross tons. So on tangent track and heavy axle load environments, fatigue always happens. In UIC environments, it sort of depends on the wear rate, which is also a function not only of the dynamic loading, but the bogey types and the curving forces and things of those sorts. But once we get to a curve, once we get to a sharp curve, what we start seeing is that the wear line moves to the left and wear becomes the dominant failure mode. So if you don't do anything, and don't do anything means you don't lubricate or you don't use a premium or a hard steel, then you're going to generally wear out on a curve due to side wear, or what we call gauge face wear. Because gauge face, because this is the gauge side of the rail. Remember, the wheel is sitting over here. So curve wear is sensitive to the radius of curvature, the hardness of the rail, the level of lubrication, and we will talk about lubrication here in a little bit. The lateral wheel rail forces, which means not only the degree of curve and the type of conicity, but the type of bogies you have. If you have a very sophisticated bogie that gives significantly lower lateral forces, that will in turn result in a lower rate of wear. And by the way, any wear you see on the rail also happens in the wheel. Wheel steel and rail steel are very similar. We'll talk about wheels in January, but wheel steel and rail steel are very similar. So the kind of wear you see on rail also happens in wheels. So if you see severe gauge face wear on a curve, the odds are, if it's a very curvy line, the odds are you're also seeing flange wear. So for example, metros for the most part replace their wheels because of flange wear, because metros tend to have a lot of curves. Oops. So if you have a lot of curves, you tend to get your wear right over there. And the wear and the wheel wears down, becomes thin, and that's a criteria for maintenance of the wheels. Wheel rail contact. I've already started this discussion with my fancy photoelastic models, and we will continue discussing it. But suffice it to say for right now that you can control the wheel rail contact. And by controlling the wheel rail contact, you can control both the rate of wear and the rate of fatigue development. And that's one of the reasons grinding has become so popular around the world for maintaining the rail. And I think I mentioned earlier that Israel Railways just, I think, spent about 25 million euros here in the last couple of years just buying a brand new rail grinder, which I think was delivered. I'm actually not 100% sure yet it was delivered. The last time I was in Israel, it hadn't been delivered yet, but it was scheduled to be delivered. And then things like lateral and longitudinal creep, which is related to the coefficient of friction, which we will talk about. I'm not going to be spending a lot of time giving you rail wear equations because there are a lot of them in the literature and there are a lot of models out there in the literature, but I just wanted to sort of give you a feel for what a model looks like. So this is a typical rail wear model, which is a function of curvature, hardness, lubrication, speed, or the relationship between speed and balance speed. In other words, are you going above balance speed, you're going to get more wear. If I have gone below balance speed, I'm going to get less wear because I'm not flanging as hard. That gets back to the lateral force issue. Rail size, whether I have joints or I'm all welded, my grade, my degree of curvature, my grade, my dynamic wheel rail force, all of these we know enter into the rail life. And if you want to just see one model equation, this is just one model that's out there in the literature. You can see the relationship is a bit sophisticated. So my function of curvature, hardness, and lubrication takes a form such as this. This allows you to calculate rail life and MGT. And then all rail models calculate life in MGT. We talked about that last week. But to convert life in years, you have to know how many MGTs per year you have. So a high density main line may be looking at 20 to 30 million gross tons a year, or if you're in a heavy axle environment, 50 to 100 million gross tons a year. A low density environment can be looking at 1 million gross tons or less. So the life of the rail in years varies very dependent on the density of traffic. And I'm not going to go through this example right now in the interest of time. You're welcome to look through this. If I'm not going through this example, then you can be rest assured that I'm probably not going to give you this equation on the exam. Any equations I give you in the exam, I make sure I spend time in class on. Okay, so that's where. Now I want to spend a little bit of time talking about fatigue. So fatigue is one of the dominant failure mechanisms we see in the railway industry, where we see fatigue of wheel, we see fatigue of rail, we see fatigue of axles, we see fatigue of car bodies. Fatigue permeates itself throughout the railway industry, and there are a lot of fatigue standards out there of various sorts. I'm just going to try to introduce this to you and give you a little bit of fatigue theory so that you get a little feel for fatigue here. So, all right. So fatigue. Now, let's start off by talking about what is fatigue. So I'm going to come back to here. I'm going to come back here for a minute. Okay. So fatigue is defined to be failure under large number of repeated loads. So there's something called low cycle fatigue and there's something called high cycle fatigue. Low cycle fatigue is when it fails after only a short number of loads. The most famous example is your paperclip. I'm sure everybody has played around with a paperclip, opening it, closing it, open it, closing, and you open and close it about 3 or 4 times, and what happens? You fail the clip. The clip fails in fatigue, right? So at that point in time, that's low cycle fatigue. High cycle fatigue is which one we really tend to see in the railway industry. We tend to see in railroad rail and railroad wheels, is where the number of cycles to failures are in the hundreds of thousands to millions. So when you talk about fatigue failure, you usually talk in terms of something called an SN diagram, or a stress number of cycles to failure diagram. So this is stress here, which you can see over here in megapascals. And this axis is number of cycles to failure. You notice this is logarithmic. Very often this scale is also logarithmic, so it's very common to see an SN diagram on a log scale. Now, how do you get an SN diagram? By running lots and lots and lots of tests in a lab. You basically cut out samples of rail and you do bending stresses, usually a rotating bending stress test, and you just test until it fractures. So what happens is, not surprising, that as you increase the stress that you apply to the steel type, you decrease the number of cycles to failure. So in this particular case, this is in PSI. I'm sorry. Let's go and do a rail steel one that has metric units as well. So in this particular case, if you had, this is about 75, 80 700 megapascals. So at about 700 megapascals, you're looking at about 700 megapascals, you're looking at about 100,000 cycles to failure. Drop it down to about 600 megapascals, and you're looking at about 200 cycles to failure. Drop the stress down to about 550 megapascals, you're looking at about 300 cycles to failure. Drop it down to about 500 megapascals, you're looking at about 1 million cycles to failure. Drop it down here to about 400 megapascals, and you're looking at about 10 million cycles to failure. At some point, when you reduce the stress, and you keep reducing the stress, the number of cycles to failure stays the same. This is called the endurance limit. The endurance limit is defined to be the stress level at which the number of cycles to failure tends to be constant. And it's usually defined, depending on the type of steel, particularly for high strength steels, is usually defined somewhere of the order of 10 million cycles. So usually at 10 million cycles, 1 times 10 to the 7th, 10 times 10 to the 6th, we usually define the endurance limit as the stress below which it will keep going forever. The number of cycles to failure basically is infinite. Now, for some structural steels, by the way, just so you know it, you'll see some places also use 2 million cycles to failure. But in the rail world, we always use 10 million cycles to failure. That's the fairly standard. I'm going to come back to this because this is fundamental for understanding fatigue, and this is fundamental to calculating fatigue life. So let's come back to fatigue, to my discussion of fatigue, and say fatigue life is a function certainly of the material properties, which we just talked about, which is the SN curve and the endurance limit. It's a function of the loading, obviously, which affects we just went through that with the SN curve. The greater the loading, the fewer the cycles to failure. And at some point, you load it high enough, it'll fracture right at that load level. And then basically you're not in fatigue, you're into fracture. But in the fatigue range, generally you're in the hundreds of thousands of cycles to failure to millions of cycles to failure. Now, remember, if you start thinking that you think that's a lot, just remember that a good freight train will have, will have 50 wagons. 50 wagons means you have 200 axles. So you got 200 axles per train. So you have 200 loading cycles per train. So, hello? 10 trains would give you 2,000 loading cycles. 1,000 trains give you 200,000 cycles. So in a year, you can start you get hundreds of thousands of cycles. So you generate the number of cycles to failure very quickly. One axle represents one loading cycle, because if you remember back from your beam and elastic foundation theory, things actually become useful at some point in time. If you look at remember your moment under one axle, I basically have a maximum moment here, I have a reverse moment here, and I go back to 0. So this is a loading cycle. So each axle represents one loading cycle. The moments, the loads are, of course, translated into stress. We see stress reversals in our bending cycles, but we also have contact stress, thermal stress, and another stress, which we will talk about only very briefly here because we don't have the time to deal everything, called residual stress, which is the amount of stress that's locked into the rail at the time of manufacture. All that, remember that nice complicated manufacturing process with those roller straighteners and everything else that I showed you? By the time the rail goes through that whole process, there's actually a certain amount of stress that's already locked into the rail. And that stress is called the residual stress. And it usually doesn't play a role because it's usually not significant in the head of the rail, but it is significant in the web of the rail. So any defect that propagates through the web of the rail usually has to take into account residual stresses as well. And then we'll talk about something called Miner's cumulative damage theory, which was how we're going to put everything together here. So dynamic loads, we already know about. We're not going to, you're all experts. You better be, because you're going to see a lot of it in applying certainly the ARIMA speed effect formula or any dynamic load model. Once you learn how to use the ARIMA model, then you can apply any quasi-static model. They all work the same until you get into the P1, P2 models, which are a little bit more sophisticated, or the fully dynamic models, but the quasi-static models all work the same, and they all take the form P dynamic equals P static times 1 plus a theta, which is the theta is the quasi-static load augment, such as, so again, for ARIMA, it's 5.21 times the speed divided by the diameter of the wheel. So if we actually did a whole bunch of tests and looked at the life as a function of rail section, we see, we can see here that the life in MGT, which can be translated in number of cycles just simply by counting the number of wheels. Can everybody hear me? I know I have some background noise. Am I still here? Can you all hear me?
Yeah.
Yes.
Am I clear?
Yes.
Okay, if the background noise gets too much, I got my gardeners out back working. One of the disadvantages of working at home, I didn't know they were showing up this morning.
Excuse me, Professor, do
yes.
you hear us? Yes. Can you explain what is stress reversals?
Oh, okay. I thought I just...
Stress reversals.
Okay, so the moment reversal. And remember, stress is nothing more than MC over I, right?
Yes.
So a stress reversal. Okay, so in a normal, okay, actually, it's a very important question. Let me spend the time, a little bit of time on this, because it's important to understand that concept. Okay, if I were to plot my, so you can see my, see if I can do it with this. If I was going to plot my stress with time, right? So this is sigma max. This is sigma min. This is positive. This is negative. If sigma max, if this is plus 300 megapascals, or like I guess it will be 300 kilopascals. No, this would be plus 300 megapascals. This is minus 300 megapascals. So I have a complete reversal, and my R ratio is sigma minimum divided by sigma maximum is equal to minus 300 over 300 is equal to minus 1. This is a complete stress reversal. And most SN diagrams, such as this, are always calculated based on R equal minus 1, a complete stress reversal, because that's how it's normally tested. However, in the railroad world, so now we go back to our beam and elastic foundation analyses, and we calculate our moment and then our stress diagram. Our stress diagram goes like this. So if I'm looking, for example, at the stress at the head of the rail, so this is minus 0.2 m, and this is m, and my stress ratio is actually minus 0.2. But we do have a reversal because we go from positive moment to negative moment. Remember the reverse moment curve we saw. So in this particular case, we have an R equal minus 2. So this is what I mean by a stress reversal. Most models, most fatigue models are based on R equal minus 1. But since the railroad rail sees R equals minus 2, we'll have to make sure we have to deal with a model that deals with R equal minus 2. By the way, fatigue theory says that stress reversals cause the greatest amount of fatigue damage. So if R is so let's say there was no reversal. Let's say I went from minus 200 megapascals I went from plus 200 megapascals to plus 50 megapascals. Then my R would be plus 0.25. There'll be no stress reversal, and my fatigue life is going to be much, much, much longer. So this reverse moment that we see from beam and elastic foundation theory is very, very critical in fatigue theory because it introduces a stress reversal, even if it's not a complete reversal. Okay. So continuing on. So this is the function. This model. This shows the life of the rail as a function of rail size. Notice life decreases with decreasing rail size or increases with increasing rail size. Why? Because the moment of inertia is greater with the heavier rail, and therefore the stress is lower. And the lower my stress, the longer my life. The higher my stress, which is the case when if I apply the same load, if I have the same if I have the same vehicles running over at the same speed over UIC 60 rail and UIC 50 rail, the UIC 60 rail will last longer because the stresses are lower because the moment of inertia is higher. Clear? Okay. Likewise, if I change my traffic, if I take the same UIC 60 rail and I run passenger traffic over it, and then I run freight traffic over it, and then I run those crazy North American 33 metric ton axle load trains over it, the life of the rail is going to decrease with increasing loading. The heavier my trains, the greater my loading. Likewise, it's a function of track modulus. We showed how moment and therefore stress is a function of track modulus. So each of these enter into effect. So when we're dealing with fatigue, it's very important to know the distribution of loading. So if I go out and I actually measure the real life load, the distribution of loading becomes really, really, really critical. So if you remember, this was a cumulative probability versus different types of traffic as a function of dynamic load. So this is my dynamic load in newtons. So what you can see here, for example, is this particular 25 meganewton, 2,500 kilo. Yeah, 1 times 10 to the 6. So about 20, this is about 25 meganewton. Force here occurs only 0.01% of the time. And this 20, so for this type of traffic, so this 20 meganewton force appears about 99.5% of the time. This 10 meganewton force appears about 70%, it exceeded, sorry, other way around. This 10 meganewton force, 70% of all the loads are less than 10 meganewtons, 30% of all the loads are greater than 10 meganewtons. For this 20 meganewton force, 99.5% of all the loads are less than this, and only 0.5% are greater than this. For this 25 meganewton force, 0.01% of the loads are greater. So if I sort of break this up into load categories, which I do over here a little bit just so it's easier to read, you can see that the range of roughly 25 times 10 to, this is 25 times 10 to the 4th, oops. So it's 200, sorry, I said meganewtons, it's 250 kilonewtons. 250 kilonewtons occurs about 0.04% of the time, and roughly 230 kilonewtons appears about 12%, 0.12% of the time, and about 19 kilonewtons appears about 1.6% of the time, and 88% of all my load is under 135 kilonewtons. So we get an idea of what our distribution is. And then if I calculate the number of cycles, this is equivalent to under 100 million gross tons of traffic. So what this says is that under 100 million gross tons of traffic, I have about 2,700 load cycles of this type, 110,000 load cycles of this type, and 6 million load cycles of this type. your initial reaction is, well, these are the dominant ones. Why do I care about these few load cycles? And then we go back to our nonlinearity of our SN curve. And what we see is that because it's an exponential relationship, only a few thousand cycles at high load can generate fatigue failure much more rapidly than millions of cycles under the low load. So for example, if this was below the endurance limit, if this equivalent stress is below the endurance limit, then the number of cycles to failure for all practical purposes is 10 million or infinite. So even though I have 6 million cycles, it's not enough to cause any sort of failure. Whereas at 25 kilonewtons, I may run this calculation and find that I only have 1,000 cycles to failure, in which case this produces a significant amount of fatigue damage. And so if I have multiple traffic types, so in this particular case, I have 3, 6, 7 different traffic types, I can combine them using this type of equation. The total number of cycles to failure is 1 over the sum of alpha I over n sub I, where alpha I is the percentage of total cycle loads at each load cycle, and n sub I is the number of cycles to failure at that load cycle. So I'm sure you all remember that this is 1 over alpha 1 over n1 plus alpha 2 over n2 plus alpha 3 over n3, etc. If I have 7, it will go out to 7. Where alpha I is the percentage of cycles at that stress level, and n sub I is the number of cycles to failure at that stress level from the SN diagram. And for this type of analysis, we're looking at longitudinal stress. So stress is coming out of the cross-section of the rail and the longitudinal section of the rail, because this is the type of stress that dominates in the generation of such fatigue defects as the detailed fracture, which caused the Hatfield derailment. And again, we're going to spend a bit of time talking about that today. So we will spend some time on that. Okay, so if you remember, the longitudinal stress is the bending stress from beam and elastic foundation theory. The longitudinal component of the contact stress, which we're taking to be 0.3 times the maximum contact stress, and the thermal stress. And again, remember, the combined stress differs at the head and at the base of the rail. Okay, which brings us back to the SN diagram. I am going to have to switch to my headphones because my gardeners have gotten very, very noisy on me. So let's hope this works. Can you hear me better now? Am I clear?
Yes.
Okay, so hopefully this will be a little bit clearer until my gardeners go away. All right, so remember, the SN diagram is the number of cycles to failure. So if I go back to this case over here, So alpha is the percentage attack and beta is the number of cycles to failure. I can calculate the number of cycles, well, actually, this is not beta, N sub I. This term here is the number of cycles to failure. So the number of cycles to failure, we get just straight from the end, from the ascent curve. So if I was at, if I was at 250 megapascals, which was over here, my number of cycles to failure will be down in the 10,000 range. If I'm at the, let me get my units right. This is 1 times 10 to the 7th. So this over here translates into 870 megapascals. That should be right. And at 870 megapascals, I'm over here at roughly 50,000. This is roughly 50,000 cycles over here. At about 700 megapascals, I would be over here at roughly 200,000 cycles to failure. At roughly 60 megapascals, I would be roughly at 1 million cycles to failure. And roughly around 450 megapascals, I will be at about 10 million cycles to failure at my endurance limit. Okay. All right, I got, so I'm going to jump forward here for a moment. We talked about stress reversal. Okay. So I can calculate my slope for this is, so this is a curve of standard rail steel. So my slope is 0.17. Check something here. Okay. My endurance limit is roughly around it's roughly around 400. Using this curve on log-log, knowing that this is a log-log relationship between stress and number of cycles to failure, I can develop an equation for the number of cycles to failure at any given stress level. And I get that by doing nothing more than doing delta y over delta x equals the slope. So if I have the slope K is equal to sigma max, or change that. My slope is equal to sigma 1 minus sigma 2 divided by N1 minus N2. And I set sigma 2 to be my endurance limit stress and N2 to be the number of cycles to failure at the endurance limit, which is 10 million. I can generate this equation, n sub I equals n sub e over S max sub I over S sub e to the 1 over k. So what this says is that the number of cycles to failure at any stress I, any stress level I want to pick, is equal to the number of cycles at the endurance limit. This says 2 million or 10 million. For real, we use 10 million. So this is 10 million. S max sub I is the stress value we want to calculate. S sub B is the stress at the endurance limit, which varies as a function of R ratio. We're going to come back to that. This becomes very important. The S sub E actually is not a fixed value. It varies as a function of R ratio, but it's a stress at this endurance limit here. K is the slope of this SN curve, which is for rail steel almost always fixed at 0.17. And I can now calculate the number of cycles to failure. Now, what's critical is what S am I going to use? My S is the combination of bending stress, longitudinal component of the contact stress, and thermal stress. So the bending stress we get from beam and elastic foundation theory, if we're dealing with a single axle, the maximum moment is P over 4 beta, and the stress is MC over I. We went through this already. You should have already, hopefully have all done this in the practice exam by now. If you have a two-axle situation, then you have one moment, second moment, and then your maximum moment combined from superposition, just like we went over in class in a couple of lectures ago. Stress reversal, we actually already discussed. For normal SN testing, it's R equal -1. For beam and elastic foundation theory, for a single axle, it's 0.2. It's actually 0.21 if you want to be technical about it. And for a bogey, where I'm combining two of them, this particular case, it's -0.29. And the thermal stress is E alpha delta T, where delta T is the difference between the rail temperature and the neutral or force-free temperature. So let's do a couple of simple examples, because by now I'm sure you're all confused. In fact, let's take a break and then we'll do some examples. Let's take a 10-minute break. Let's come back around 20 after, and then we'll do some examples.